Hello, welcome everyone. My name is Lars. I'm a consultant in Munich, and I'm very happy to be here. This is my first time in Japan, and I'm really enjoying the conference so far. So good job to the organizers. Also, I have to apologize for the pun in the title. Apologies to whoever had to translate that to Japanese. Basically, the point I'm going to make is that property testing is also proper testing. And of course, this is by far not the first talk on property testing. And I would like to focus here on some of the internal details that some of these libraries have to offer and some of the advanced features that are out there. There's a whole lot of other resources out there on how to come up with properties and how to add that to your existing code base. But this talk has a slightly different focus. I would like to explore some of the internal details together with you. But of course, there may be people in the audience who have no idea what property testing is. So I have a few moments to explain this basic concept to you. All right. So the basic idea is that instead of writing examples by hand as you would traditionally do in unit testing, you just write abstract properties that take in some variables. And then you just let the framework instantiate those variables for you. So instead of saying, well, call this function f on 0, and on 1, and on 5, and on 99, maybe some other numbers, you just say, call this function on an integer, and then the testing framework will somehow do that for you. And I believe in Japan, this is known as omakase, right? You go to a restaurant, you just say you want some food, and then you let the chef, like this chef, give you some food to you. You don't necessarily know what kind of food you will get, and you don't necessarily care, otherwise you wouldn't have ordered omakase. I hope I'm pronouncing this correctly. So the idea with property testing is the same thing. You just specify that you want some integer or some string or whatever kind of type, and then the testing framework will go ahead and give that to you. Okay, so here's a short example. This is from ScalaCheck, which is, I think, the most commonly used property testing library in Scala. And you can write so-called properties. And this property says, well, I want 3 integers, and I call them x, y, and z. And then I want to test that x times y times z is the same as if I first multiply y and z and then multiply x. So this is what the mathematicians would call associativity. This is a very basic law of arithmetic, and of course we all assume that this holds. And if we were to write such a multiplication function, maybe we have come up with our own number type. We wouldn't necessarily want to specify the x, y, and z all the time in our tests, so we just say ScalaCheck, please say for all x, y, and z. And what the test framework will do, it will just call this property 100 times with different input values. And in this example for integers, of course, this law holds. So it will print, OK, passed 100 tests, which means that there were 100 values that ScalaCheck came up with and just call this property and verify that it holds. Now, what you see in this property, it looks basically like a normal test, but you have some parameters out here. So that's the basic structure. Now, what happens if we change that into float? And it's the same property, x times y times z, just with different parentheses. But we have a different type. Instead of int, we have floating point numbers. And ScalaCheck will tell us that this does not hold, because floating point arithmetic on your computer works differently. So it does not satisfy this. And then it will tell you falsified after 2 passed tests, and it will give you the arguments that it has tried out for which it fails. And in this case, the precise reason for the failure doesn't really matter, but I mean, you can look it up, how floating point arithmetic works. But this is basically the output that the test framework will give you. And I challenge everyone to come up with these problems yourself when you're writing unit tests. It's very unlikely that you will come up with all these corner cases, but these property testing frameworks are very good at finding these kinds of problems. All right. So I've already mentioned that that this is not the first talk on property testing, and it's also not, ScalaCheck is also not the only library for Scala, and other languages have these tools too. So this is really a very common theme in testing. And many of these libraries have similar features, and I would like to outline some of these commonalities. First and foremost, most importantly, you have automatic and custom generators. So you, for example, you can tell the framework, please give me integers, right? And it will just give you whatever integers it could come up with. But it also allows you to say, well, maybe I have a function that only works on positive integers. Or maybe I have a function that only works on prime numbers. In that case, you can always specify a custom generator. Also, you can filter inputs, right? So you can say, well, what if I have a generator for some big set of values, and I'm only very interested in this very small set of values? For example, I could say, well, give me food, and then I just want the sushi rolls. So I could say, well, the generator for food, and then I filter out everything that is not a sushi roll, and that will be discarded. And my function will only ever see these inputs here, and not the others. Also, what's very interesting is shrinking of counterexamples. So what does it mean? If you see here, it found a counterexample, so it found some inputs that make the property false. Let's assume you have a function or property that takes as an input a list, and then it found a list of 20 elements that violate some condition. Now that would be very hard to debug, because you have to look at 20 different elements, and you have to keep track of that while you're looking through your code. So what these frameworks can do is they can try to minimize the counterexample. So you say, well, this is a list of 20 elements that's failing. Maybe if I just take the first half of the list, maybe it's still failing. So it tries it again with 10 elements. And if it still fails, good, you just got a shorter counterexample. And it will keep doing that. Maybe it finds a list of just 2 elements that's failing. And the same goes for integers. For example, let's say your function is failing for 1,000. Then it will try to divide it by 2, and will try it with 500. Maybe it's still failing with 500, and your debugging just got a little easier. The remaining bits, classification of inputs and input and property labeling, basically allows you to debug your tests, so to speak. It will basically give you better error messages or better diagnostics. So you can, for example, say, well, I've been running this property, and 38% of the values I've just created are even numbers. And then you maybe think, well, why is just 38? Shouldn't it be like 50%, something like that? So these features are a little bit more advanced, and they allow you to troubleshoot problems you may have in the tests themselves. And also give you better diagnostics in case something is wrong. Right. So this is a non-exhaustive list of these various libraries. So if you use a language that's on the slide, you have a few options. And there are even more languages which have these libraries. I did a search on NPM 2 days ago for JavaScript, and I think I found just like 20 property testing libraries or something like that. So this is there's a lot of different libraries out there that can do that, and chances are, even if you work in an exotic programming language, somebody has created such a library. Maybe not if you're working with COBOL or something. I'm not sure if COBOL has a property library, but most languages these days that are in active use have such a thing. All right. So now that we have looked at the basics, I would like to take a deep dive and explain a little bit how these libraries work under the hood. And of course, there are some differences between those libraries. Some work slightly differently than others, but the basic idea is sort of the same across many of them. So I'm going to use the terminology from ScalaCheck here, because I'm assuming most people here use Scala and would be using ScalaCheck maybe in their own code base. So let's stick with that. So the question is, how do we come up with values? So I've shown you a property on the second slide, which just says I need 3 integers. But how do we produce these integers? And the answer is we could generate them at random. And a thing that generates stuff at random is just called a generator, or gen for short. So we have this box here, which is a generator for type R. So it's a generator that's able to produce values of type R. And in order to do that, it needs 2 inputs. The first input is some kind of random number generator. So it takes some sort of random seed, which is obvious. If we want to produce something at random, we need some random seed to start with. Also, we take in some parameters, which for the purpose of this talk, you can imagine is just a size. So the generator takes a size as an input, which tells it the size of the thing that it should generate. So if you have a generator for lists, and the size is 10, it will always generate lists of size 10. If the size is 5, it will generate lists of size 5. And then when the value comes out of this, it will be stuffed into the property and evaluated. Now, the way this usually works is that the testing framework will test or will generate 100 different values, and it will start at size 1, then go to size 2, size 3, and so forth. It keeps increasing the size, and then maybe testing 10 values for each size. So you have 10 lists of size 1, 10 lists of size 2, and so on, and then until you reach 100 different tests. But obviously, all those frameworks allow you to customize that, so you can set a custom size, custom frequency of values, whatever you like. Okay, so that's very basic, and all of these libraries have a lot of generators built in. But there's one challenge here. What if we don't want to just generate plain values? What if we want to generate functions? Imagine you're writing some code that looks up some kind of item by name and maybe returns a price. So you have some products, and these products have some price, and you want to implement a shopping cart that computes the total value of all the items. And then you would maybe do a database access, so the type here takes a string in and returns a future of int. Now you can implement the shopping cart with that. But the problem is that it's bad for testing, right? So when you want to test the shopping cart in isolation, you don't necessarily want to do these database lookups. In particular, if you test the shopping cart, you don't actually care what prices there are for the products. You just care that there are some prices for products. So the question is, can we generate a random implementation of this method? Can we actually generate a random value of type string to int? And the answer is yes, we can do that. But let's first try to figure out how we could do that. So the first idea that comes to mind could be that we can just pre-compute a table, right? So we have a string goes to int, and then we can just like create a big lookup table for all the different strings that we could think of, and then returning some random integer prices. Now, of course, this is impractical because, as you know, there are infinitely many strings. So you would need infinitely many memory chips in your computer to save that table. So we can't really do that. So this idea is out. What if we would just make up values on the spot? What if we generate just a function and then the function keeps track of how it has been called in the past? So let's say if I call it with A, then it just says, well, I give you back 5. And then you call it with B and it says, I give you back 10. And then if you call it with A again, it will look up what it has generated before and say, oh, this is 5 again. In principle, we could do that, but it's side effecting. And also, it could be a memory leak, because this table could just grow and grow, and depending on the use case, we might not be able to clear out that table. So that's not good. We could also just say, well, let's just create constant functions. Whatever the input is, whatever item you're trying to look up, always return 10. But of course, if you're implementing some complex logic for your computations, then that's not good enough, because you might want to test some corner cases and some complicated things. What if the price of an item is 0, for example? I mean, you might not run into these issues. And property testing is, the idea behind property testing is that you want it to run into corner cases so that you can improve your tests. Okay, so none of these ideas work, but there is an idea that works. And this one is called cogen, or longer cogenerator. So a cogenerator is basically the opposite thing of a generator. You can think of it more as a consumer instead of a generator. And the co in front of this comes from mathematics, essentially. So you have a generator and a co-generator, which is the kind of the opposite of a generator. Now, how does it work? Well, if we generate a function from string to int, we know that the int that comes out of the function can only depend on the string that it received as an input. But when generating the function, we don't know the inputs yet. So what can we do about that? We can use the inputs to perturb the random generator, right? So we take a random seed, we just generate it at random, and then the function takes an argument, and then we use that argument to somehow change this random seed somehow, and then produce a result from that. So I have a small diagram here again. It's the same diagram from a few slides before. This is what you have with a normal generator. You have a generator of type R, and it takes in a seed. We just assume that the size is fixed somehow, and it produces a value that can be stuffed into the prop. But we can also put this cogen before, so T would be the type of the input arguments. So we take the seed, pipe it through cogen, then we get a changed or perturbed seed, and then we put that to the generator and generate a value. And expressed in Scala code, this would just look like this. So a co-generator is just this interface that has a single method, and it takes in a seed, and it takes in a T and produces a new seed. Okay, so I know this is a little hard to understand when just looking at the slides, so I've prepared a small demo to just exercise these features. Okay, so I'm just using a Scala shell here. And basically what I'm doing is I'm importing the standard ScalaCheck library, so there's nothing else going on here. It's just plain ScalaCheck and some imports from that. And the first thing we can try out is we can try to see how a normal generator behaves, a normal random generator behaves before we start working with functions. So I define some default parameters, and then I ask for the generator that gives me positive numbers. And then I can ask that generator to give me some values. Forgot to define the seed, so I still need the seed. And as you can see, a seed in ScalaCheck consists of 4 different integers. I don't know what the idea behind this is, but this is just how it is implemented. Now I can ask for a random integer if I just call the generator, and as you will see, this is always the same thing. So there's no side effects going on there. The seed is a purely functional, immutable thing. If I were to ask for a fresh seed, I would have to call seed.next, and then I will get some different numbers. Okay? So this is functional, and there's no side effect going on here. Okay, so now let's try to fiddle around with the seed. So we can ask for the cogen. And let's say we ask for the cogen of string, so a thing that is able to process string inputs. And then we can say, well, what happens if we use this perturb function to change the seed if we read an A? Then we get a different seed, and we can also try to read a B, and we get another different seed. And this is precisely the idea. If we take a string in, it will change the seed somehow in some way, and then we can create fresh values. So if we go back to the generator, right, if we just take the unchanged seed, we get 82. But if we change the seed before cogen.terp, we now get a different number, 37. And there's no side effects. If I call it with A again, I will still get 37 back. Now if I call it with B, I get 58. different number. And the nice thing about this is that there's no hidden table, no hidden side effects going on. This is all completely functional, and it requires very little memory. So the only thing that you need to store is basically the seed. So you don't have to explode it into a very big table in your memory. Okay, so we can generate plain values, integers, strings, other things. We can generate functions, everything at random. So the question is, should we do that for every single thing, every kind of data that we could come up with? Do we want to generate everything at random? Well, there's pros and cons, as usual. So one of the pros is that, as I've mentioned before, this is very likely to run into corner cases. So in Japan, this is not a big surprise, but developers in Germany, for example, are very surprised when their systems receive some kind of Japanese or Chinese symbols as input, and then the systems will crash. So ScalaCheck will just create these characters for you. It's no problem. It will find these corner cases, right? And what I wrote here is likely to find input you didn't think about, and this is just applies to all sorts of corner cases, right? Would you have thought of calling your function with plus infinity or minus infinity, for example? Maybe not, but ScalaCheck would have thought about that. It can also cover a wide variety of input very easily because of the size. It starts with size 1 and then just keeps increasing the size, and then it may just call your function with a list of size 20. And maybe your regular unit tests would just call it until size 5, but maybe with size 20 it takes a lot longer to process and you have some performance problem hidden there in somewhere. So this is also very nice to spot these kinds of problems. Now, of course, there are downsides also. Sometimes the big problem is that this code is not deterministic. So you run your tests locally, you commit your code, you push it to your repository, and then your CI tool builds the code again, and then maybe finds a failure, because someone else may have a different random seed than you would have on your system. So this is not very good, because you usually want your tests to be deterministic, right? If they succeed once, then they should succeed another time. But if you use random testing, I mean, it says that in the name, right? If you use random testing, then your tests are random. So that means you can get random failures. Now, most of these test frameworks have a workaround for this, which is they will print you the seed if they find a failure. So if the test fails on someone else's computer, they could tell you the seed that made it fail, and then you can copy-paste that seed to your own machine and then can reproduce the problem. Right. Often high discard ratio means if you use automatic generators, if you don't write your own generators by hand and then you filter them out, it may mean that you have to filter a lot of different values. For example, you want prime numbers. And you would just say, well, give me an integer and then filter out all the non-prime numbers. The problem is there are many non-prime numbers. So it may just be the case that out of 100 generated numbers, only, I don't know, like 20 of them are prime. So maybe that's not good enough for your use case. It basically means that the test framework has to work a lot harder to come up with valid inputs, and your tests may be very slow. Also, existential properties are difficult, and that means if you want to have a test, let's say you have a function f, and function f is very expensive to compute, and then you wouldn't say, well, I want to find a particular input such that the output has some property. Then you would need to figure out what kind of input would trigger that kind of output. So this is a little harder to implement because most of these libraries, they just do stuff at random, and there's no strategy behind it. It's just random testing, and it doesn't know what your function looked like. It's just a black box. So I would like to explain a little bit about how this last downside could possibly be fixed. And I've been talking a lot about random testing, but it's also possible to have non-random property testing. And this basically works by enumerating values. So in Scala, you could implement that as the following interface. It's called enumerable. So a type T can be enumerated. And it basically just returns a stream of values. So instead of saying, well, give me 5 random integers of size 3, it just would say, give me all integers of size 3. Or maybe let's use lists as an example. Give me all the lists of size 3, or all the lists of size 5. Unfortunately, as far as I'm aware of, there's no such library for Scala, but there is one for Haskell, which is called SmallCheck. And it supports a lot of things from logic. So you can use quantifiers. You couldn't say there exists an x such that some property holds. There exists a unique x such that property holds. Or you can just, as usual, say for all values some properties hold. And also it can do implications. So you can say if property P holds, then also some other property Q holds. And you can also mix and match. So you can have quantifiers that are nested in implications. So you can say, well, assuming there is an x that satisfies some property, then also something else would need to hold. Okay. And I don't have time for the demo anymore, so I'm going to go to my final point. What if I want to test polymorphic things? The initial example I showed was for 2 types, for int and float, this multiplication law. But sometimes I write code that works for all different types. For example, what if I implement a custom collection like lists and want to test that the reverse operation works correctly, that the append operation works correctly? It wouldn't really be there would be no point in testing that for lists of ints or lists of strings. You want to test it for arbitrary kinds of lists. So how can we do this? Well, we could try to write such a polymorphic property, but then ScalaCheck wouldn't know how to instantiate this property. So what kind of type A should there be? And should we come up with fresh types? So should we use existing types from the Scala standard library? Or should we just make up our own types? Well, there is a workaround for this, which is using existential types. So existential types in Scala are basically just type members in a trait that have no definition. So we can define a trait that's called type, and it contains just an unknown type T, and maybe it also has a name for easier printing, and it also has a generator for T. Now, if we see such a value of this type, we know nothing about T. We have no idea what T is, but we can generate values of it. And this is something I would like to show. So this is again something that can be built very easily on top of ScalaCheck, and I have some code that I will paste into now, and it's irrelevant what the code does, so you can just ignore the first bit of copy-paste. And what I can do now is I can write polymorphic properties. So I can define properties that have some unspecified type, and the system will fill in some types for me. So I've defined here a property that I just called prop poly, because it's polymorphic. And then if I check it, it will figure out, well, there's some type I need to fill in there. And if I put in a type that is called 2, then it will fail. And this is some very interesting stuff, because suddenly you can write your properties completely in a polymorphic fashion, and you don't need to take care of int or strings or whatever. The system will do that for you. And the kind of mind-blowing fact about this is that you can use ScalaCheck not only to generate values for you, but it also can generate types for you. Now, why is this useful? Let's say you work with data pipelines and you have implemented something on top of Spark or on Flink or whatever, and you have some custom operations on your data pipelines. Then you sometimes want to say, well, I have the stream here, and I want to map this stream from type A to type B, so I want to come up with some random functions from A to B, but I don't care what A and B are, so you can basically use these frameworks to generate random data pipelines for you, which I find really interesting. It's also useful if you're writing a compiler and want to generate input for that compiler. There's a whole separate talk from Eric at FlatMap from earlier this year in Oslo. He goes on about that data pipeline stuff. So he explains in a very detailed way how to generate random data pipelines using ScalaCheck. And I don't think there is currently a published library that does that, but it's kind of easy to implement for yourself, and it's also very customized to your problem domain. So it's, at the moment, it's a little unclear how to pull that out as a separate library. Okay, finally, I would like to give an outlook into what other features are out there for property testing, because this is still a space of tools that is heavily innovated in. So there's still a lot of development going on there, and there's new things being published about this. So, for example, one thing that's a little bit older already is law management and checking. So if you're working in a code base that uses type classes heavily, these type classes usually have invariants and laws attached to them. And if you have many implementations, many type classes, it can be a little bit cumbersome to list all the properties every time you write a test. So there's a library that allows you to bundle up multiple different properties and test them all at once. There's also a kind of library that does what's called integrated shrinking. So in ScalaCheck, generation of values and shrinking of values are two completely separate processes. And in particular, you can write generators that cannot be shrunk. So you can have values that you cannot really shrunk, and there are some other libraries that try to make that a little bit better and take care of the shrinking for you. So they will basically sort of like keep track of a tree of values that they have generated in the past. Automatic classification of counterexamples is an interesting thing because let's say you have a function that works on two lists and it has a bug if the two lists are of the same length. Or maybe it has a bug if the two lists are of a different length. And there are some tools that try to infer that kind of stuff from your test failures. So it will run your test with like 100 values as usual. Then it will look at all the counterexamples and will try to find commonalities between those counterexamples. And it will say, well, if you give two things with the same length, then you will have a problem. And this will make debugging much easier. Automatic generation of properties is also interesting because let's say you write a lot of code, but you don't have any tests, and you have no idea what you want to test, then there are tools that will try to come up with things to test for you. So they will basically generate properties, test these properties, and then tell you which of these properties hold. So that's very interesting. And of course, there's always the step to go. The lowest step is basically unit testing with customized examples that you come up with. There's property testing, which generates values at random for you, and then there's proofs, and proofs will cover all the different inputs. Not just 100 values at random, not just the 100 smallest values, they will cover all the input values. So of course, proofs are also possible, and there are tools that allow you to import, for example, Scala code into a formal system and then carry out proofs on your code. And then you can be extremely sure that there are no counterexamples for that. All right, so that concludes my tour through property testing, and I think we have time to take some questions. Do we have time for questions? Okay.
ありがとうございました。スカラプロップスというプロパティベーストテスティングを作っている、はい、ケンジです。ご存知だと思うんですが、はじめまして。はい。そのスカラ界では今回のトークと直接若干内容がそれる質問になるかもしれないんですけども、スカラ界隈ではスカラチェックが今もデファクトスタンダードで、最後の方に紹介してもらった機能などいろいろハスケルでは、新しいもっと先進的な機能が試されてたりするんですが、でもスカラチェックに取り込まれるのが遅かったりとか、他のスカラチェック以外のプロパティベーストテスティングのライブラリも出てきたりして、今後そのスカラチェックに機能を入れていくのか、他のをもっと新しく作ってスカラチェックをよりも他のを流行らせていくのかとか、そのあたり、例えばキャッツでもスカラチェックを使っていると思うんですけど、今はそのあたりどう考えているか、個人的な、意見を聞かせてほしいです。
So, if I understand the question correctly, it's about the role that ScalaCheck plays in the Scala community, and if there are any possible alternatives with new features coming up. So it is true, ScalaCheck is the default. The vast majority of people use it. And in particular for the type-level ecosystem, for CATS and Spire and many others, it is just a standard library to be used. And it would be very hard at this point to change it to something else. I'm not saying it's impossible, but for now, I don't see any short-term plans. There's ScalaProps, of course. There is Hedgehog, also a port of the Haskell one, which is currently not recommended for production use, I think. I think there's a disclaimer in the repository, so this is also not ready for production yet. And there is also, in the new Scala test release, there's also some property-based testing in there. I haven't looked at it yet. But it is true, inside type level, we have talked about this a lot, and we are still talking about this, if ScalaCheck would need to be evolved to have more features, or if it would be time to maybe embrace a different one, or maybe create a new one. And the only thing I can tell you at this point is that we don't know yet. There's still heavy discussion going on, and inside type level, some projects will probably switch to a new one. So some projects also don't use Scala test, they use Specs or Monix test. So there's no consensus yet. So we can maybe talk about this afterwards, but I don't think there's any consensus yet on what to do about this.
はい、ありがとうございます。
Thank you very much for that. Thank you. Thank you. Thank you very much, Lars. Thank you.
Interesting talk. So, do you think we should replace all of unit tests with property-based tests, or use property-based tests and old-style unit tests depending on circumstances?
Of course, more property-based tests are better because they will exercise your code more. But also there are some use cases where it's just very hard to come up with concrete properties. Sometimes you just need to do the regular unit testing and specify some examples. What I found in the past is that it also matters how you develop your software. If you write your software or your code with property tests in mind, it will be much easier to write property tests. If you don't, then it's going to be a lot harder. So for existing code bases, it's going to be very hard to introduce property testing. If you're writing new code, you should probably keep property testing in mind, and then it will be much easier to write the tests that way. But I think you will never be able to live without unit tests. There will always be cases where you cannot just generate random values.
Thank you very much.